So what I'm going to do here is give you a little head start on your homework on question 10. I'm going to go ahead and work through part A for you. And what you'll need to do for parts B and C may not necessarily mimic what I do here, but I want to illustrate for you the idea of using our basic definitions in order to prove something is true. So we want to show in this case that for all n vectors v, that the infinity norm is less than or equal to the 2 norm. Okay, so first of all, to prove something like this, if you try to just show that it's true for some specific vector v, that's not a proof. You just showed it for one specific vector. We want to show it for all vectors. Alright, so on your homework, hopefully I won't be seeing any specific vectors being used for your explanation. We want to keep things general. The best place to start on this type of question is, you're just going to answer based strictly off of the definitions of these norms and maybe use some properties of norms along the way. Alright, so off to the side, I went ahead and copied down our definition of the infinity norm and the 2 norm. The infinity norm was the biggest entry in the vector in absolute value. The 2 norm, you add up the entries squared and then take the square root of that sum. And then the properties of norms are also listed. So we know that either of these norms will satisfy all of those properties by definition of a vector norm. They have to satisfy those things. So some of those may be helpful to us as we go through number 10. Also, I just kind of threw in, we've got the triangle inequality for vector norms. I went ahead and wrote down the triangle inequality for just regular old absolute values. It's the exact same idea. That may be helpful to you in some of your question 10 homework that you'll be doing. Alright, so let's start with this first inequality. We want to show that the infinity norm for any vector is always going to be less than or equal to the 2 norm. Alright, so this when we prove these inequalities, it's nice because we've got different ways of measuring the size of a vector, different norms, and it's good to have an idea of how these norms are related to each other. So knowing that the infinity norm is always less than or equal to the 2 norm, that can be helpful to keep in mind in particular situations. Suppose, say for example, the 2 norm of some vector is small, then you know by default that the infinity norm will also be small because the infinity norm is less than or equal to the 2 norm. Alright, so just understanding these relationships can be helpful in certain applications. Alright, so for this particular inequality, starting off with my definitions, knowing what the infinity norm and the 2 norm look like, this 2 norm has a square root going on and it has all of the entries being squared and we're adding them up. It may help a little bit here to just make things look a little bit more similar between the 2 norms. The nice thing, something nice I can do here is if I square both sides of this inequality, the inequality is still true. So the infinity norm is less than or equal to the 2 norm. That's true if and only if the infinity norm squared is less than or equal to the 2 norm squared. And the reason I'm doing this here, you won't necessarily do this in all of the parts to question 10, but it's just convenient here because on the right hand side, by squaring it, I'm getting rid of this square root, and on the left hand side by squaring the infinity norm. I'm taking that max entry and squaring it. And so then I've gotten rid of the square root, and now I'm looking at the max entry squared and comparing it to the sum of these entries squared. And once I do that, it's really already almost obvious why the infinity norm must be less than or equal to the 2 norm. All right, but if it's not obvious, I'll go ahead and write out the details. So let's write down, just by definition, what is the infinity norm squared. Well, first, maybe it'll help if I say, let's suppose that the infinity norm, which by definition is the max of the absolute value of the entries in the matrix. Let's say that max value was, let's just call it v sub j. Where j is just some index between 1 and n. So this vector v is in Rn. All right, so if v sub j is our biggest entry in the vector, then the absolute value, or I'll say the v norm, or the infinity norm squared, then we can call that absolute value v sub j squared. And now obviously v sub j is going to be less than or equal to what we get when we add up v sub j squared with all the other entries in the vector squared. So this is clearly going to be less than or equal to absolute value v1 squared plus absolute value v2 squared plus, somewhere along the way we run into this vj squared. Right? It's obvious that this inequality holds because we've got the vj squared showing up here, and we're adding to it a whole bunch of things that are bigger than 0. Okay? But what have I just written down? What I've just written down is exactly the sum of the squares of the entries. So this is exactly the 2 norm squared. Okay, so look at our inequality here. We've got the infinity norm squared is less than or equal to the 2 norm squared. And if that's true, then it must also be true that the infinity norm is less than or equal to the 2 norm. Okay? So this is just one example of how we can use our basic definitions to prove one of these inequalities. Let me go and show you part A. There were, on number 10, there were 2 inequalities that they wanted you to prove. Let me go ahead and show you the other one on the next slide. Now again on this one, here I'm showing the 2 norm is less than or equal to the square root of n times the infinity norm. I'll go ahead and start the same way I did the last one. If I square both sides, the inequality is still true. So this is this inequality holds if and only if the 2 norm squared is less than or equal to, if I square this whole right hand side, the square root of n squared will just be n. And then we've got the infinity norm of v squared. All right, so again, you won't necessarily do this extra step of squaring both sides on all of the parts to question 10, but here I think it's just convenient because it cleans up the work a little bit. So let's just start with the definition of the 2 norm. Again, it's this is all you're doing on this homework question. Just start with the definition and see what you can come up with. Here, the 2 norm, if I square it, then again, that square root goes away. So the 2 norm squared is just the sum of the absolute value of the entries squared. Okay. Now, similar to what we did on the last one, we know that somewhere in this sum is one of these v sub i's is the biggest v sub I in absolute value. So again, let's suppose we know what that biggest one is. So let's say v sub j is the biggest entry in this vector in absolute value. So for I equals 1 to n, if I look at the absolute value of v sub I and pick out the biggest one of those, then I'll call that v sub j. Alright, so if v sub j is my biggest one, then clearly this sum is going to be less than or equal to what I would get if I just added up v sub j over and over again, because v sub j was the biggest one. Alright, so now if I add up v sub j n times, then this is equal to n times absolute value v sub j squared. But v sub j, absolute value of v sub j, remember that was our biggest entry in the vector. And so by definition, this thing right here is our infinity norm squared. So this is n times the infinity norm of v squared. So again, we get fairly easily the inequality that we want. The 2 norm squared is less than or equal to n times the infinity norm squared. And if that's true, then by default the 2 norm must be less than or equal to the square root of n times the infinity norm. Alright, so I just wanted to illustrate for you guys how to use the definitions to do some of these proofs for number 10. So make sure you stick to the definitions, stick to the properties that we have for norms, and I think parts B and C will go fine. Also make sure number 10 carries over to page 177. There's a last part to that you need to make sure you do. It says, for each of the above inequalities, identify a non-zero vector v bigger than with n bigger than 1, where equality holds. All right, so we're showing that these inequalities, these are less than or equal to. Find some specific case where you actually have the 2 norms being equal. All right, so make sure you do that for each one of the inequalities to finish out question 10.